So welcome everyone. Thank you for joining. So today's talk is going to be about combinatorics, and we are going to be looking at combinatorial proofs in the beginning, and as we go on, we'll start to look at a more algebraic aspect and how you can combine algebra and combinatorics. So if you're attending, I'm assuming you've read the abstract. So this is basically a more detailed version of the abstract. So it's just going to be introductory combinatorics. So even if you have seen these ideas before, I hope that I'll give you a new perspective. And if you walk away with a deeper understanding, I call it a success. So broadly, there are three parts. The first part deals with some well-known sums and identities involving the binomial coefficients, and we'll prove these without any algebra. And we'll focus on how they are basically generalizations of the much simpler Pascal's identity, basically the one which Pascal's triangle is built upon. The second part deals with binomial coefficients with negative upper indices. So although there is no straightforward combinatorial way of interpreting these, I will provide a combinatorial way to approach them so that the extension of the definition seems much more natural. And we'll be using the inclusion-exclusion principle here, which also I'll be going through the proof of. So even if you don't know what the inclusion-exclusion principle is, that's completely fine. And a bit of algebra will be required to fill in the details, because if you don't do that, then you lose rigor. So to not lose rigor, I'll be using a bit of algebra, but it will only be for filling in the details. And in the third part, we'll go all in with the algebra. And in the second part, we are only flirted with this idea of combining combinatorics and algebra. So we'll be using derangements, and we'll be counting how many derangements there are. So the standard way of doing this is, of course, using the inclusion-exclusion principle, but that's not what we'll be doing, because inclusion-exclusion principle quota will get over in the second part. And hopefully it will also show you some relations between derangements and permutations, like the set of all permutations, by showing some similarities between the factorials and subfactorials. And at the end of the talk, I have given some points which you can try to explore on your own. So there are questions, and some of them are just like nudging you towards exploring certain aspects on your own. So hopefully that will give you some more insight. And after that, I've also put some further reading material, so you can check that out if you are interested in that. And that will one of those questions and one of those articles will give you some connection between combinatorics and linear algebra, or not exactly a connection, but rather how you can use linear algebra to do combinatorics. And I'll be emphasizing on how one can come up with these ideas on one's own. So that aspect I'll be focusing on throughout the talk. So if you ever feel that some step has come out of the blue, you can feel free to let me know, and I'll try to make it a bit more intuitively obvious. So let's get started, and we'll start off with the binomial coefficients. So this is the standard notation for binomial coefficients. I know most people use NCR, but hopefully you'll get used to this, because in the entire talk I'll be using this notation. So you might already know the factorial representation. And one of the most basic identities for these binomial coefficients is Pascal's identity. And the Pascal's triangle is basically built upon this identity, hence the name. And it's pretty easy to prove. So the first proof is completely algebraic. And basically you just take the common denominator. And this proof almost makes the identity seem like a coincidence, that these cancellations happen just by coincidence. And there's nothing special behind this identity. The second proof uses the fact that binomial coefficients are the coefficients of the powers of x in the expansion of 1 plus x to the power n. So that gives a slightly more natural way of looking at it. So that gives you some insight about why this should be true. So I'll be looking at a more literal aspect of this. So n choose R can basically be read as choose R objects from n. So I can read this equation as choosing R plus 1 objects from n plus 1 objects is the same as either choosing R from n or R plus 1 from n. So if I interpret this, does it make sense? And if it does make sense, is it the proper kind of sense, or is it like if I squint my eyes and turn my head sideways a bit, it kind of makes sense? So we'll explore this aspect, and from here we'll basically the first two parts of the talk will basically flow out naturally. So it turns out it does make sense. And the way we'll make sense of it is, suppose you have n plus one objects and you want to pick r plus one from those. So one way is to pick n plus one and pick r from the other n objects. So here I've color coded it a bit. And this covers all the sets which have n plus one in them. And the other case is that n plus one is not in the set. So you don't pick n plus one and you pick all the r plus one objects from the n objects. So that's the other case. And if we count the number of ways of doing it this way, then for the first case, you have NCR ways because the first choice of n plus one is fixed. So there's only one way to do that. And there are NCR ways of choosing R objects from n objects. So you get this. And likewise, in the second one, you have n choose R plus one because from the green ones, you're picking R plus one. So since it's an exclusive OR case, you add them, and this also covers all possible cases. So these are two things which you should always check in a combinatorial proof that there are no double countings and that it covers all cases, because these are the two places where you can most likely go wrong in a combinatorial proof. So since this covers all cases of choosing R plus one objects from n plus one, we get this Pascal's identity. So it flows out pretty naturally from the definition of these binomial coefficients, and you don't have to do too much jugglery to see this. And another perspective is that we have this identity, and basically what this identity does is that it reduces the top index by one, and it converts the bottom index into two parts. So one part is r and the other is r plus one. But we get another part which is r plus one. So we can split that again using the identity. So we go to the second step, and now we have this new identity which has three terms on the RHS. So can we make sense of this? So again, in the same way, we can make sense of it. So first case is that you pick n plus one. So it's blue, and I've color coded it here. And you pick r from these green ones. So I've color coded it here. And the other case is you don't pick n plus one and you pick n. So the cases where you don't pick n plus one are basically divided into two. So if you don't pick n plus one, you can either pick n or you can't pick n. And that's what I've done. So you pick n and you take r from the green ones, or you don't pick n plus one and n, and you pick r plus one from these. And if you count the number of ways there are to do this, you get this exact identity. So if you add all of these ways, you get n plus one choose r plus one. But then you can ask the question, what if I go further? Because there is another r plus one term. So I can split it again, and I can keep splitting all the way till I get to r plus one choose r plus one. So as you can see, there are all the terms have r at the bottom except for the last one, and the upper index of the last one and the second last term remains the same. So you can see that the patterns continue. And from going from the second last line to the last line, basically what I've done is r plus one choose r plus one is just one, and r choose r is also one. So you can just replace r plus one choose r plus one with r choose r, and the identity remains the same. And now you have this nice pattern of the upper index going down by one at every step. So you get this nice identity. So how do you interpret this combinatorially? If I write the statement in English as before, so to pick r plus one from n plus one, I can let n plus one be the maximum choice. So basically I'm choosing r plus one objects. So the biggest object can either be n plus one, or it can be n or n minus one, or so on till r plus one. Obviously you can't go smaller than r plus one. So if you look at it combinatorially, you get this nice visual representation that you take n plus one as your maximum, or you take n as your maximum, or n minus one as your maximum, and so on. And if you count the number of ways there are to do this, once again, you get the exact quantities which we wanted. And from there, our identity flows out naturally. So the other perspective on this will look the same at first glance, but it isn't the same. So what I've basically done is I can either, so I have n plus one objects, and I basically divide them into two parts. So the first part on the left is n plus 1, so it just contains n plus 1. And on the right, you have the numbers from 1 to n. And what I can do is, if I want to pick r plus 1 from this whole set, then I can pick 1 from the left and r from the right, or 0 from the left and r plus 1 from the right. So this looks like the previous case, but I have not color coded it in the same way. So in the previous case, I had colored this as red, but I have not done that here for a reason. So now if you look at how many ways there are to do this, obviously you'll get the same expression, but you'll get these extra factors of 1 choose 1 and 1 choose 0. But they are of course both 1. So they cancel out and you get the same identity as before. N choose r plus n choose r plus 1 is n plus 1 choose r plus 1. But if I take it a step further, what if I put 2 on the left and r on the right, sorry, n on the right, and I want to pick r from this. So either I can pick none from the left and all from the right, or I can pick one from the left and the rest from the right, or I can pick two from the left and the rest from the right. So I think there's a typo over here. It should be 0 and r, 1 and r minus 1, and 2 and r minus 2. So you can, if that's confusing you, the visuals will hopefully help you. So I can pick 2 from the left and r minus 2 from the right. That's one case. I can pick 1 from the left and r minus 1 from the right, or 0 from the left and r from the right. And this again covers all cases without any double counting. So you should make sure that that is the case. And if you count the number of ways to do this, you get 2 choose 2 and r n choose r minus 2. And likewise, you see that as this left coefficient decreases, like the bottom index of the left coefficient decreases, the right one starts increasing. So it goes from 2, 1, 0, and this goes from r minus 2, r minus 1 to r. And you add all of these and you get n plus 2 choose r, because that is basically what we have done. We have picked n plus 2 objects from n plus, sorry, r objects from n plus 2 objects. And now we can take it a step further. So instead of having one or two elements on the left, I can go all in and I can make it into a variable. So what if I have p variables on, or p numbers on the left and n numbers on the right, and I want to pick r. So either 0 from here and all from here, or 1 from here, rest from here, or 2 from here, rest from here, and so on till r from here and none from here. So that's basically it. So you can write it as I, where I goes from 0 to r. So now if we count the number of ways there are to do this, you have p choose I over here because p numbers and you're picking I of them. And on the left, on the right, you have n choose r minus I because you have n numbers and you're picking r minus I. And if you add all of these, so of course this is an AND case. So you have to multiply this, and you add all of these OR cases. So you get this nice identity. And the thing I want you to notice is that if you sum the indices on the top, you get this thing. And if you sum the indices on the bottom, you get this thing. And this latter part of summing the indices on the bottom is going to be important for us in the second part as well. So I'd like you to remember that. And you can also go over in your mind why this should make sense, that the sum of the top indices gives you this top index and the sum of the bottom indices here gives you this bottom index because of the setup itself. So that's how the setup works. So now we'll go to the inclusion-exclusion principle, and we'll first go through a quick derivation, and after that we'll go forward with the second part. So the inclusion-exclusion principle is basically the generalization of this well-known formula where you want to find the number of elements in the union of two sets. So you basically add up the number of elements in each of those sets and you subtract their intersection. And that makes intuitive sense because you have the elements which are in this intersection are counted twice. First you count them in A and then you count them in B. So there's some double counting. So you have to get rid of that double counting. And of course, you get this identity. And you can extend it to 3 sets and you basically get this form. So the usual form you might have seen is with the sizes of A, B, and C and the sizes of their intersections. But if you write it as this one set at a time, two sets at a time, three sets at a time, you can generalize this pattern later on. And you also get this alternating sign pattern, which is again there in the generalization. So what this does again is the same. You basically take all of the individual sets, but then you've ended up double counting some of the parts. So you have double counted the intersection of A and D, you have double counted the intersection of A and C, and the intersection of B and C. So you subtract them to get rid of the double counting. But then you have subtracted this middle part thrice. So you have to put it back in and you basically get this identity. So that's why it's called the inclusion-exclusion principle. First you include, then you exclude, then you include, and so on. So you can generalize it by continuing this pattern. You have one set at a time, minus two sets at a time, plus three sets at a time, minus four sets at a time, and so on. And you can go all the way till k sets at a time, where k is the total number of sets you have. And this basically gives you this nice summation identity, but the common form we use it in is this complement form. So if the size of this union is given by the sum, the size of the complement will be given by the size of the universal set minus the size of this union set. So you can see that there is a plus here and not a minus because that has been taken care of in this exponent right here. So this form is actually more useful in combinatorics, but there is actually a further special case of this which we'll be using. So the proof for this generalization, I won't do it here, but you basically use this identity to your advantage. So after the talk, you can go through it. And at the end, I've also given a hint of how you can do this proof on your own. And the Wikipedia article on the inclusion-exclusion principle also has a nice proof, so you can check that out as well. So, as I said, in combinatorics, we'll be using a different form of this identity, which is a special case. So, the special case we have is basically the one where the size of all the sets is the same. The size of their intersections taken two at a time is the same. Size of intersections taken three at a time is the same, and so on. So you get these equalities. So over here you have each and every set in this equality. Here you have each and every intersection of two sets. Then in the next one, you'll have intersection of three sets, and so on. And we can give these names S1, S2, and so on. And basically, just a formal way of writing that is given at the bottom. So you can read that later. So in this case, special case, the binomial coefficients turn up because the number of ways of choosing I distinct sets from a family of k sets is k choose I. So it's literally just the definition of the binomial coefficients. So since the intersection of all the, so if I take A sets and I take their intersection, that intersection size is going to remain the same regardless of what exactly those sets are. It only depends on how many sets there are. So I can basically just replace this I sets at a time with k choose I times si, and the rest of the identity remains the same. So you have the same universal set and you have the same powers of -1. And this is the form which we'll be using. And in fact, in the form which we'll be using, we'll write this universal set as S sub 0. So the size of the universal set is as S sub 0, so that it fits a nice pattern and you can include that term in the summation itself. So now let's get to the second part of the talk. So the second part basically deals with this sum S of ABR, which is defined this way. So if you are comfortable with summation notation, you can look at this. And if you are comfortable with the dot 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 notation, then this is for you. So you basically, at every step, you first start off with A choose R and B choose 0. And then at every step, you reduce this index and you reduce this index and you increase this index. So as you can see, it goes from A to A-1, A-2, and so on till A-R. And this goes from R, R-1, R-2, and 0, and 0, 1, 2, so on till R. And the sign is also alternating. So this alternating sign will actually look familiar because we just saw the inclusion-exclusion principle. And that actually will help us solve the problem. So for now, we'll assume that A and B are greater than or equal to R, of course. So you want A greater than or equal to R because otherwise this term will have a negative index up top And we don't want that, because although I have mentioned that we'll be discussing binomial coefficients with negative indices, we are not there yet. So right now we need this to be positive, and so a has to be greater than or equal to 0. Sorry, r. And likewise, b has to be greater than or equal to r, because otherwise b choose r wouldn't make sense. You'll have this index being bigger than this index. And this is again a case which we'll handle later on. But for now, we'll assume that d is greater than or equal to r. And also we want r is greater than or equal to 0, because otherwise you'll have a negative number over here, which we don't want. So these assumptions are all obvious. And the not so obvious assumption which we'll be making is a minus b greater than or equal to r. So over here, if you just look at this sum, you might think that there is no reason why we might assume this, because we are never subtracting b from a. So why would you need a minus b greater than or equal to r? So you are right. There is no dependence of this assumption on this sum, but we'll be assuming it anyway, and you'll see later on why we are assuming it. But for now, just go with it. So as I said, we have seen this pattern of the alternating sign and this binomial coefficient times something. So this something is also a binomial coefficient, but for now you can neglect that fact and just think that there is some expression over here and a binomial coefficient, a nice binomial coefficient over here. So by nice, I basically mean the upper index remains the same and the lower index goes through all the values. So this we have seen in the inclusion-exclusion principle as well. So maybe there is some connection, and maybe we can use the inclusion-exclusion principle to evaluate this. So let's see if we can do that. So it turns out that the answer is yes, and we can. So first of all, we'll basically bring it in the same form as the inclusion-exclusion principle, because if we don't do that, then how can we compare that? So firstly, one thing which you might notice between this summation and this summation, the biggest thing which you can notice is that I have replaced this with S sub I, and I've mentioned that equality over here. And another thing which you may notice is that here the upper indexes are, and here it is B. So from where did I get those extra terms? So I have basically accounted for those extra terms by saying that S sub I is equal to 0 whenever I is greater than R. So any term which is not over here will be 0 anyway. So we can just add it back in. And so you get this expression. So yeah, that's what I've said over here, that if you compare it to the inclusion-exclusion principle, in the inclusion-exclusion principle, we had used K. So if you replace K with B, you get this exact scenario. And as I said, for the I equal to 0 case will be U. So your universal set is the I equal to 0 case. And now all we need to do is think of a family of P sets which have their sizes and the intersection of the sizes given by these S sub I, because that is the main part, right? If we don't find any sets, then we can't apply the inclusion-exclusion principle, no matter how similar the two expressions look. So to do that, we'll be noticing some similarities of this sum, which we have S of ABR, where this upper index is also going down, which we don't like, with this nicer sum, which we had already solved, which is A plus B choose R. So over there, I used N and P. So if you just replace N with A and B with P, you get this. So one thing which you can notice between these two is that the sum of the bottom indices is R in both cases. So even though there are so many differences between these two sums, that this power of -1 is there, so sign is alternating, and the other thing is this A minus I, which is the biggest thing which you notice just at first glance. Despite that, there is a similarity, and this similarity is what we'll be exploiting, and we'll use this to find our sets A1, A2, so on. So for now, we'll ignore this alternating sign and we'll just look at what we get by ignoring the alternating sign. So we won't evaluate the sum you get by ignoring this, but we'll just pretend it's not here for the sake of simplicity for some time. So this is basically the A plus B choose R identity. This is what we have done. So you pick I from the left and R minus I from the right. So what you have done is you've picked R overall, but you have to take in the other cases as well. So if I have zero, if I pick 0 from the left and R from the right, 1 from the left and 1 R minus 1 from the right, and so on. So now what we have in this new sum is, so basically what we are trying to do is get this expression, this a minus I choose r minus I times b minus times b choose I, without this power of minus 1. So what combinatorial process gives me this expression? That's basically the thing we are trying to figure out. So what you can do is you can again have a plus b elements. So you have b elements on the left and a elements on the right, just like over here. So the first term is b choose 0 times a minus 0 choose r minus 0. So that's this. And so what you can do is you can pick 0 from here and r from here. But in the next step, you can't do the same thing as over here, because that will give me b choose 1 times a choose r minus 1. Sorry, a choose r minus 1, but that's not what we want. We want a minus 1 choose r minus 1. So for that, I need to get rid of one element from the right. And it doesn't really matter which one, because we just care about the fact that there are a minus 1 and we are picking r minus 1 from those. So if I just have b on the left and a minus 1 on the right, and I pick 1 from here, r minus 1 from here, I'm sorted. I get the exact term which I was after. And likewise, if for the third term or second term, however you want to call it, you can pick 2 from the left and r minus 2 from the right. So now what you're doing is you're choosing 2 from b, so you get this b choose 2 term, and you're picking r minus 2 from a minus 2, so you get the a minus 2 choose r minus 2 term. So once again, we have gotten the expression which we wanted. So if we just keep continuing this pattern till the I equal to our case, we are basically done. This will give us all the terms which we were after. So the only problem is that we don't have the alternating sign as of yet. So we'll come to that later. But now one thing you might notice is that this thing of removing one element is a bit cumbersome. So over here it was nice because we were picking the same, we were picking different amounts of elements from the same two sets. But here our sets themselves are changing. So that is a sort of a problem which we hadn't encountered before. So maybe if we could get rid of that, it would be much more helpful. So what you can notice for that is that here you are picking two elements and you are getting rid of two elements. So what would happen if the two elements which you had picked were these two elements? Then you wouldn't have to worry about this. So you have already picked two elements and you're picking r minus 2 more. So that would help us out, because then our sets wouldn't be changing. We wouldn't have to do this getting rid of the sets. But then, of course, the number of elements would be a problem. So you have a plus b elements, whereas you want b and a minus 2. So how do you deal with that? So what we can do is, instead of assuming that the A and B sides are separate, we can assume that the B side is actually contained within the A side. So now you have B elements over here. So you can see that if you take the difference of these two, you get B minus 1. So there are B elements in blue and A minus B elements in green. So basically what I've done is I've picked these blue elements and I've overlapped them with some of these elements. So now, if I pick some number of elements from here, then I'll automatically lose the same number of elements from the total, which is A. So I can pick I from here, from the blue ones, which is the same as over here. You are picking I elements from the blue ones. And once you pick those, you have automatically gotten rid of I elements. So that A minus I, which was troubling us, is automatically there because you have picked I elements and you have a total of A. So now you have A minus I. And from those, you pick R minus I more. So first you pick I from B. So that gives you B choose I. And then you pick R minus I more. So you don't include the ones which you have already picked. So now you are picking R minus I from A minus I. So I hope everyone got this point. If there is anyone who has confusion with this, you can let me know. I'll go through it again. So everyone is fine with it? Okay. So this now gives us a hint towards how we can apply the inclusion-exclusion principle. So firstly, we can figure out what the sizes of the sets are. So in the IEP expression, S1 was basically the size of these sets, right? It was mod A, mod A1, mod A2, and so on. So S1 is the size of these sets. And in this case, our S1 is A minus 1 choose R minus 1. So that gives us a hint because that is this expression is not only a number, it's also an action of sorts, right? You're picking R minus 1 elements from A minus 1 elements. So there is some sort of action associated with this number, which gives us a hint towards what the sets would be. And this expression is what you would get if you wanted to pick R objects from A, where one is already chosen by default. So if the statement is not very clear, you can consider this analogy of, let's say you have A players and you want to pick a team of R players from this. But you know who the best player is, so you obviously want the best player in your team, so you just pick him by default. So there is no freedom for you in picking that one player because he's just going to be in your team because he's the best. So now what you are doing is you have to, so you already have one player selected for your team, and now the total number of players has reduced by one because that player has come into your team. You don't need to consider him anymore. So now what you're doing is you're picking R minus one players from A minus one players. So you get this exact expression. So maybe that is the action which you're doing. And you may say that, okay, why would you even think of this scenario? Why won't you just take some set of A minus one elements and pick some R minus one from that? And that is because in the original setup, we have A elements over here. So if I take A minus 1, so if I'm choosing R minus 1 from A minus 1, then the problem with that is which one do I ignore? So that problem comes up, and you can't really answer that unless you reframe your picking action in terms of A elements so that you are not ignoring anyone. So this statement, it's fine if you don't read because it will be much clearer from the visuals which I'll be showing. So the set A1 can be defined to be the set where you pick A by default and then you pick R minus R minus 1 from these. So A is your captain. And the other case is A minus 1 is your captain and you pick R minus 1 from the rest. So that again gives you that same A minus 1 choose R minus 1 expression. And every way of picking R objects this way will go in your A2. And likewise, you can have A minus 2 as your captain. So then that will be A3 and so on till A minus B plus 1 being your captain. And that will give you AB. So you can take a look at this slide for some time so that it's completely clear to you because the next argument is based on. And moving on. So now that we have defined our sets, this you might recall that this was all just guesswork. We haven't actually proven that if you apply the inclusion exclusion principle on these sets, you do actually get the expression you are after. So that is something which I've left for you to prove. So again, emphasizing on the fact that until now, we have just done guesswork. There was no proof till now that these sets are actually the ones which we are after. So that you have to prove separately. So that also brings about the aspect, and hopefully that shows you that math is not just about doing rigorous stuff and like just formulae. Sometimes you just do guesswork and you check if your guess works. And when you are checking whether your guess works, that's where the rigor part comes in. So you have to do guesswork and you have to be rigorous. You can't do just one. So moving on, let's call the union of these sets as A for easy reference. And this A has some way of choosing R elements from A elements, if and only if that way contains at least one of these elements. So if you go back to our visual, you see that in one way, so if the way of picking R objects from A objects is in A1, then A will be in your set for sure. If it's in A2, then A minus 1 will be in your set for sure, and so on. So if you're taking their union, then that must mean that at least one of these yellow elements is in your set, the union, which is A. So at least one of these elements from A to A minus B plus 1 is chosen in this union. But so yeah, so that's what I've written over here, that you must have at least one of them. But the sum which you are after is given by the size of the complement of A. So if you go back this IEP expression, you basically see that in between the mod signs, you have the complement of the union. So the sum which we are after is actually given by the size of the complement. So how do we find the size of the complement? Well, it's simple. If any element of A must contain at least one of these, then any element which is not in A must contain none of these. So the size of A complement is given by the number of sets, which the number of ways of picking R objects from A objects, which have none of these elements. So how many elements are these? These are B elements, and you had a total set of A elements. So if you're not picking B elements, then you are picking R from these A minus B elements. So how many ways are there to do that? You have A minus B, choose R elements. So we get that S of ABR is given by A minus B choose R. And now I hope that you can see why we had assumed A minus B is greater than or equal to R, because otherwise this expression wouldn't make sense. So again, I'll give you some time to think about this logic, and after that we'll move on. So if anyone wants me to go to the visual slide for a minute, you can tell me and I'll go back to that slide. The slide where I had colored A in yellow and A minus 1 in yellow, that one. And moving on. So now we'll come to this assumption of A minus B is greater than or equal to R. And now I'll say that this is not actually a necessary assumption. If we redefine our binomial coefficients to be able to handle this scenario where this upper index is smaller than the lower index. So M is greater than N. So we can assign this to be 0, and then this sum will work. So if you assign it to be 0, then you have your identity equaling 0 when A minus B is lesser than R. But then, of course, you may say that this is just a definition. So if I just define the binomial coefficients in a different way, that doesn't change the value of S of ABR. So how do I justify the fact that this changing of definition doesn't change the sum itself? So the way you see that is basically by noticing that this definition makes combinatorial sense, because if I have 10 objects, I have 5 objects in a set and I want to pick 10 from that set, how many ways are there? 0 ways. So saying that if the lower index is greater than the upper index, then this kind of scenario happens where you're choosing, let's say, 10 objects from a set of 5 objects, which of course there are no ways to do that. So this must be 0. So this definition makes combinatorial sense, and since our proof was entirely combinatorial, we can adjust our arguments to fit this case. So once again, in your own free time, if you're interested, you can try to go back to that proof and justify that this definition makes sense, and if A minus B is actually lesser than R, this definition works. But we still have to assume that A minus B is greater than or equal to 0, because then for sure this won't make sense. So this is a scenario where there are no ways to pick uh, 10 objects from 5 objects. But if I ask you to pick 5 objects from minus 1 objects, that question doesn't even make sense. So we can't even assign 0 to that, because the question is nonsensical. So you can't assign a value. So we must assume that A minus B is greater than or equal to 0 for now. But something must be bothering you, of course, because the original expression for S of ABR, which is given by that summation, doesn't actually give you any problems if a minus b is lesser than or equal to r, because over here there is no dependence on the quantity a minus b, but somehow through the combinatorial process we have brought it about. So even though our combinatorial process doesn't work for a minus b is lesser than or equal to 0, that doesn't mean that the sum doesn't exist, right? The sum is pretty well defined. So we have not solved the entire problem. We have only solved half the problem. So how do you solve the rest of the half, where a minus b actually happens to be lesser than 0? So an idea is that since this extension seems so natural, where the RHS suddenly doesn't make sense, but LHS makes sense. So what if we define the LHS to be the RHS in this problematic case? So for negative upper indices, so n is lesser than 0, n is negative. In that case, we can just say that n choose r is defined to be S of ABR, where a minus b is n. So if n is minus 5, for example, then you can have S of ABR where a minus b is minus 5. And in that case, S of ABR will be perfectly defined as long as we maintain this inequality, because if this is not satisfied, then we have problems in the sum itself. So we don't want problems in the sum. So we can just assume that a and b are greater than or equal to r, and you pick any values of a and b such that a minus b is equal to minus 5, and you're done. This sum makes sense, so you can make sense of the binomial coefficient. But a slight problem with that is that you're making the assumption that S of ABR does not change if A minus B does not change. So our combinatorial argument only proved that if A minus B is greater than or equal to 0. So if the combinatorial proof works, which is when A minus B is greater than or equal to 0, this statement is true. But when it becomes negative, our proof breaks down, so we can't say that this is actually true. So how do we handle this? So our definition seems to make an inherent assumption which we haven't proven. So one way is, of course, you just fix a value for a and b. So you can say that we'll take a is equal to r and b is equal to r minus n. So notice here that r minus n is greater than r because n is negative. So in this case, you can evaluate the sum for a equal to r and b equal to r minus n. And you can say that whatever value that gives you is your n choose r, where n is negative. But again, that is a problem, because if this extension is actually as natural as we claimed it to be, then this shouldn't be a problem, right? It should actually, so this assumption should actually be true if the sum is actually as natural an extension as we claimed it to be. So maybe we should try to prove it. So I won't prove it here. I'll leave it to you as an exercise. But what you can do is you can use these two identities. So at first glance, it may seem very complicated, but if you just take a minute to absorb what this identity is saying, then you will see that if x minus y is greater than or equal to 1, then this identity is literally just the Pascal's identity. So this is Pascal's identity, right? So if I replace the upper index, which is n, with x minus y, then for this case, where x minus y is greater than or equal to 1, so n is greater than or equal to 1, Pascal's identity works perfectly fine. We can prove it combinatorially. So this identity is justified. And the way you look at that is for reducing n. So over here, we are going from n to n minus 1 at the top. So if I want to reduce n by 1, I can do that by either decreasing x or increasing 1. And in the identity, you can see that over here you have x and x minus 1. So I have reduced x by 1, and that basically reduces n by 1. And likewise, over here, you can see that r converts into r and r minus 1, just like in Pascal's identity. And likewise, the other cases, I can increase y. So for increasing y, you can see that over here you have y plus 1, y plus 1, and likewise r becomes r and r minus 1. So this identity is actually the same as Pascal's identity. But once again, you have a problem over here, because this only works for x minus y greater than or equal to 1. So how have I claimed over here that x and y can be any numbers greater than or equal to 1 or 0, depending on whether you have minus 1, etc. So this over here, I have placed no such restrictions on x and y, that x minus y must be greater than or equal to 1. I've said that it works for all values of x and y. So for this, you have to prove it algebraically using the definition of S of ABR. So with a bit of manipulation in the summation form of S of ABR, you can show that this identity works. And if you prove it algebraically, there will be no assumptions of x minus y is greater than or equal to 1, because you won't be using the fact that we derived that A minus B choose our formula previously. So without using that formula, you're proving this identity, and then of course it will hold for all values of x and y. So yeah, so that will give you these identities, and from there you can prove that if A minus B is constant, then S of ABR is constant. So now finally we have proved that our definition works. So the one assumption which our definition was making is completely justified using algebra. So we have n choose R defined by S of ABR with all of this stuff, which as I mentioned previously. So you have n being negative, so upper index is negative, and you have A minus B equal to n, so that A minus B choose R becomes n choose R. But this actually also works for n greater than 0. But we won't go there right now, but you can see later for yourself that even if n is positive, this identity still works. And that is, of course, what we proved using the combinatorial approach. So just a quick review with some visuals so that you can recall. So first we started off with this seemingly arbitrary sum, S of ABR, but then we noticed that it has some similarities with the sum which we had previously seen. So this is the expression for S of ABR, and this is the expression which we had seen before. And as you recall, this evaluates to the sum of upper indices, A plus B, choose the sum of the lower indices, which is R. So A plus B choose R. So this is that expression. So using that expression and the similarity between these two sums, we basically came up with this visual approach of first you pick 0 from here and R from here, then you pick 1 from here and you pick R from the green ones, and you get rid of this one element, and likewise you keep going. But then we realized that instead of getting rid of one element every time from the right hand side, we can just assume that these B elements were actually contained within the A elements. So that makes sure that we don't have to deal with this getting rid of elements thing. And then we did this assigning a captain thing, where which basically helped us find our sets A1, A2, so on. So A1 is the set where A is your captain, A2 is your set where A1 is your captain, and so on. And that gives us the sets which we were after. So that inclusion-exclusion principle handles the rest. It does the heavy lifting for us, and we get the formula A minus B choose R for this. And then S of ABR gave us a way to extend the binomial coefficients to negative upper indices, and we used a bit of algebra to fill in the details. So now I'll give you some time to look at this, and the next part is the third part, where we'll be going a bit deeper into the algebra aspect. And moving on now. So now we come to a more computational aspect of this problem. So we have extended our definition successfully, where if this upper coefficient is negative, upper index is negative, then we can handle this scenario and we can evaluate it using this sum, which is perfectly defined using binomial coefficients which have only positive indices. But the problem is that this is a pretty difficult way to evaluate this binomial coefficient, where you have to multiply two coefficients and then you have to take the sum over some number of terms. So that is pretty cumbersome. So can we simplify this a bit? So the first thing you might notice is that the appearance of A in this expression as of A plus n R doesn't actually add a free variable to the equation. So changing the value of A doesn't change this RHS, just like it doesn't change the LHS. So we can just pick a value for it. We can pick the simplest possible value for it. And in this case, the simplest possible value happens to be the smallest possible value. So we can't handle A is lesser than R, but we can handle A is equal to R. So what if we let A equal to R, and then this A minus I just becomes R minus I. So this coefficient is R minus I, choose R minus I, and this basically vanishes because it's 1. So now you just have a sum of a single binomial coefficient. So now this is better, but you still have to sum over R terms. So that is not ideal either because R terms is a lot. So can we simplify the problem further? Well, turns out we can with a bit of induction. So, since there is no immediate way which pops out of solving this problem, and we can't solve it combinatorially either, at least not in that's at least not in the scope of this video or this talk, because you have these powers of -1. So that makes it a bit hard to work with. But what we can do is, since we have no clue, we can just plug in some values for R. So we'll take small values of R, and for simplicity, we'll replace R plus N over here with P, so that we just have a single variable. So minus N choose 0 is just P choose 0 because there's just one term in your sum. So that is just 1. Then if you take minus and choose 1, then you get two terms in your sequence. So you can also see that it's actually just minus and choose 0 minus p choose 1, because this, if I change, if I increment r, I basically get the same sum but with an extra term. So I basically get minus n choose 0 minus p choose 1. So you get this expression, and likewise you go to the next one, and you get a new expression. And every time you factorize these with using their roots, you see a pattern. So first you had 1, then it became p minus 1, then it became p minus 1 times p minus 2, and you get this 2 in the bottom. And of course, there's also an alternating sign. So you get 1 minus 1 plus 1 and so on. So if you think a little bit, you will notice that this is actually just p minus 1 choose r. So if I have r equal to 0, this is p minus 1 choose 0. This is minus p minus 1 choose 1. Then this is p minus 1 choose 2, and so on. So a bit of induction, and you can see that this formula works. And this formula which we have gotten, if you get rid of this minus 1 to the power r, also gives you the number of ways in which you can have r variables summing to a total of n. So basically it's the number of, if I have a number of positive variables and I want their sum to the n, then how many ways can I do that? So this binomial coefficient gives you that. And there is a way to combinatorially look at it, and I wouldn't be going over it right now, but you can do a bit of research. So one way is to look at the uh, expansions of the inverse of 1 plus x. So 1 over 1 plus x, 1 over 1 plus x square, and so on. So over there, you would expect to see these minus or the negative index binomial coefficients, of course, because you are raising 1 plus x to the negative power. And the binomial theorems, at least for the positive powers, tells us that you can expand it using powers of x in a certain way using the binomial coefficients. So you can also do that using uh, negative indices in your coefficients. And that is another way to look at this extension of the binomial coefficients uh, with negative indices. So I won't go over that right now, but you can explore that aspect on your own. And that will give you a combinatorial way to understand this binomial coefficient. So now we'll come to the third part with derangements, and we'll take a non-standard approach as we have been so far. So derangements are a special type of permutations, and in particular, they are permutations with no fixed points. So that means no one goes to their original position. So if the permutation is of numbers 1, 2, 3, so on, then no number goes to its own place. So 1 doesn't go to the first place, 2 doesn't go to the second place, and so on. So you can look at these examples just to make sure that you've understood what the idea is. And the problem which we'll be exploring is how many derangements are there. So if I have n elements and I want to find the number of permutations which satisfy this condition of no fixed points, how many ways can I do that in? So let's say that the number is d of n, and we'll be using this later on for computation. So I'll give you some time to go through these examples. So we'll use combinatorics and algebra, as I said. So some combinatorial thinking, let's compare this with permutations. So just like before, we look at what we already know. So in the second part, we already knew the a plus b choose our identity, and we compared the new sum which we had with that identity, and that gave us some insight. So can we do a similar thing over here? So with permutations, it's pretty simple. If I want to find the number of permutations of n plus 1 objects, what I can do is I can fix one element and I can permute the rest. And then I can fix another element, permute the rest, and so on. So every time the number of ways of permuting these green objects is n factorial, and I'm doing that n plus 1 times. So one goes in the n plus 1 position, two goes in the n plus 1 position, and so on. So I'm doing it n plus 1 times. So I basically get n plus 1 factorial is equal to n plus 1 times n factorial, which we already know. So can we take inspiration from this to work with derangements? So we'll do something similar. We'll fix n plus 1 of 1 in the n plus 1 position and derange these elements. So there are t of n ways to do this, and there is of course one way to fix one over here, and then we'll fix 2 in the n plus 1 position and derange these, then 3 in the n plus 1 position, derange the rest, and so on till n plus 1 in the n plus 1 position and derange the rest. But it is pretty easy to see why this doesn't work. So the first most obvious problem is that in this last step, you're putting n plus 1 in the n plus 1 place, and that automatically disqualifies your permutation as a derangement no matter what you do over here, because you already have one element in its own position. And a second more subtle way of which is causing a problem, which we'll see later on, is in the green part, and that will also give us an insight into how we can solve this problem. So why does it not work? So first, let's have some notation. So for every number I, we'll denote the ith position with this square bracket I, and we call it the home of I. So basically, square bracket 1 is the home of 1, square bracket 2 is home of 2, and so on. So a derangement is when everyone has a home, but no one goes to their home because no one goes to their own place. So that's a bit sad, but it is what it is. So to see the problem, what we can do is first consider the case where one goes to the n plus 1 position. So that is basically this case right here. So one is in the n plus 1 position and it's fixed. We are not going to move it, and we are moving the rest. So over here, we assume that the other elements, the green elements, which are 2, 3, so on till n plus 1, are moving around in derangements of n elements. So these are n elements, and we assume that they're getting deranged. But that is not the case, because although, so over here in this, I've I've put this exactly one home in bold. So that may seem obvious, because if I'm deranging n elements, then of course each one has to have its own position. So if I'm deranging 1, 2, 3, so on till n, then there is a first place and there is exactly one first place. There is a second place and there is exactly one second place, and so on. So everyone has a home. It's trivially true. So why is this trivial thing in bold? Because that is where we have gone wrong. So 2, 3, so on till n have homes, but n plus 1 doesn't have a home because 1 is sitting in the home of n plus 1, right? We put 1 in the n plus 1 position. So n plus 1 doesn't have a home in the effective sense, because as we are moving these elements around, n plus 1 never goes in the n plus 1 position. So it essentially doesn't have a home, even though all of these have homes. So that is where we are going wrong. That is why the number of ways of moving those green elements around is not actually d of n. So how can we fix this problem? So first, let's also notice that 1 is a home which doesn't have an owner. So so the owner of the square bracket 1, which is the element 1, is sitting in the n plus 1 position. So it doesn't require its home. So essentially, this home has no owner and it's an unowned home. And likewise, we have a number which has no home. So we have a home which has no owner and a number which has no home. So we'll do some social work. What we'll do is we'll give this number without a home. So we'll say that n plus 1 will have a pretend home of square bracket 1. So what if we do that? So firstly, we can't say that n plus 1 can never go in the first position. So a derangement, if you recall, is a permutation where no one goes to their own home. But we can't say that n plus 1 can't go to the first place because that is perfectly allowed. So this is just a pretend home, it's not an actual home. So n plus 1 can indeed go to its own home. And the other cases, of course, where it doesn't go. So those are the only two possibilities. So what if we say that possibility 1 is where we fix n plus 1 at its home? So we won't move it around, and 1 also we won't move around. These green elements will move around. And now we can say that these green elements are getting deranged because each element has a home, each home has an element, and each element has exactly one home. So this is actually a derangement. And you have n minus 1 elements over here. So 2, 3, so on till n. That gives you n minus 1 elements. So number of ways of moving these around is t of n minus 1. So the other case is where n minus 1 is not at home. So it is not in the first place. So in the first place, you have some number which is not n plus 1. So now we can say that we'll derange all of these. And in the derangement, we'll assume that the home of n plus 1 is square bracket 1. So that basically assigns a home to n plus 1. And since we know that the cases where n plus 1 is already in the first position have been covered, so we don't want n plus 1 in the first position. So it is essentially a derangement. So all of these green elements have a home and all the homes have an element. And likewise, this special case of the yellow home, we have assigned an element n plus 1 to it. And likewise, n plus 1 also has a home. So now you have n elements and each element has a home. So you can derange it. So how many derangements? D of n. And once again, you can try to think about why there are no double countings in this. And we also cover every case. So as I said, those are the two things which we should always make sure when doing a combinatorial proof. So I'll give you some time to absorb this and make sure you are not confused, because after this, it's all just algebra. So this will give us a recurrence relation for D of n, and then we'll do some algebra. So this was the whole discussion was when 1 is fixed in the n plus 1 place. So that gives us d of n minus 1 plus d of n base, as we saw over here. So if you just add these two cases, you get the total number of ways where 1 is fixed over here. So now we can also put 2 in the n plus 1 place, 3 in the n plus 1 place, and so on till n in the n plus 1 place. And each one of them will also give us the same number of ways, right? Because it doesn't really matter which element you put there, because the rest of the procedure of doing the derangements is going to be the same. So we get this relation between t of n plus 1 and d of n and d of n minus 1. So unlike the usual permutations, you can see that we need the previous two cases to get the next case. And that makes it seem familiar to the Fibonacci sequence, because, and you also have this same pattern of summing the previous two terms, and you're not doing anything crazy with them. But the fact that we have this n at the front makes them much more similar to the factorials. And in fact, if you replace d of n plus 1 with n plus 1 factorial, d of n with n factorial, and d of n minus 1 with n minus 1 factorial, this relation actually holds. So if you do the algebra with a bit of simplification, you can see that n plus 1 factorial is n times n factorial plus n minus 1 factorial. So that might seem surprising, but it shouldn't, because the whole combinatorial approach which we took to get to this relation actually works for permutations as well. So if I just permute these green elements and permute all these elements over here, I will get all the possible permutations of n plus 1 objects where this object is fixed. So you will have to do a bit of thinking to fix a few problems which occur with that. But ultimately, you'll see that once you have fixed those problems, you get this exact relation between the factorials. So once again, you can do that on your own after the talk. So now, one thing which may come to your mind is if factorials and these derangement numbers, as they are called, satisfy the same relation, how is it possible that they are unequal? And we know that they are unequal because there are permutations which are not derangements. So the most obvious case is, of course, 1, 2, 3, 4, so on till n. So that is, of course, not a derangement. Every number is at its home. So the number of these two can't possibly be the same. So how is the recurrence relation the same? So the trick is in the base cases and in the language of differential equations, the boundary conditions. So you should never forget your boundary conditions. So the sequence of factorials starts with one factorial, which is 1, 2 factorial, which is 2, and so on. And then this derangement sequence starts with d of 1, which is 0, because you can't derange a single element. It has to go in its own position. And for two elements, you have two derangements. Uh, so you have two numbers, 1 and 2. So 1, 2 is not a derangement, but 2, 1 is a derangement. So you have a single derangement in that case. So your base cases are different, and that's where this difference between the two sequences comes. So since there is, so the recurrence relation basically tells you the asymptotic behavior of these sequences, right? And if you have worked with analysis enough, you might have started to give more weight to the asymptotic approach, asymptotic behavior. Oops, what did I do? So you might have learned to give more weight to the asymptotic behavior of a function than anything else. So since the recurrence relation is the same, we might expect their asymptotic behavior to be similar, and hence we might expect that their ratio approaches something, and we'll look at that later. And because of this similarity between these two, where the recurrence relation is the same, and so their sizes are approximately the same, and combinatorially speaking, also the way we derive this recurrence relation is the same. So there are quite a few similarities between these two. So that's why some people use this factorial n notation to represent d of n, and it's called the subfactorial. So in the notation also you can see that they are pretty similar. So now we'll go back to solving the problem at hand, which is finding the number of derangements, which is finding d of n. So one thing which you can try to do is you just use the recurrence relation we have, this one, and you basically start to replace d of n with, you write d of n in terms of d of n minus 1 and d of n minus 2, and then you write d of n minus 1 in terms of d of n minus 2 and n minus 3, and so on. So you can just keep iterating that process, and you'll get some formula for d of n plus 1 in the end. But things get pretty ugly if you try that. So I'll leave it to you. If you're curious enough, you can try it. We'll use an alternative approach. So since we saw that d of n and n factorial have similar growth, it is reasonable to expect that the ratio might converge to something, as I said. So maybe this will even help us to solve the problem, because if we take their ratio, the subsequent ratios will keep getting closer. So what we can do is we can divide both sides by n plus 1 factorial, and that will give us the ratio of d of n plus 1 and n plus 1 factorial over here. And of course, n plus 1 factorial has n factorial and n minus 1 factorial as factors, so they will appear over here as well. So we don't need to worry about these terms separately. The n plus 1 factorial which we use for this will cover these two as well. So what I've done here is basically some algebra after dividing by n plus 1 factorial. So we start off, we'll give this ratio a name, r of n. So r of n is d of n by n factorial. So dividing these two gives you r of n plus 1 over here. And then over here, you can write n plus 1 factorial in the bottom as n plus 1 times n factorial. So that will give you n plus an extra factor of n plus 1 over here, and n factorial will combine with the d of n to give you r of n. And likewise, you can take out an extra factor of n, and you'll be left with n minus 1 factorial, and that will combine with this to give you r of n minus 1. And now you can see obviously that there is going to be a cancellation over here. N and n will go away, so you just get 1 over n. And likewise over here, since the numerator and denominator are pretty similar expressions. They are pretty close to each other. It makes sense to say that we'll write it as 1 minus something. So you can say that it is 1 minus 1 over n plus 1. And you can see that easily by doing this manipulation of adding and subtracting 1. So this is the final form, which I have written over here. And now, as I said previously in passing, that the difference of these ratios might converge to 0 because the recurrence relation is the same and the factorials and subfactorials grow more or less the same way. So maybe the difference of these ratios is also important. So what if we use the difference of these ratios and we call it delta of n, delta for change? So if I move this R of n to the LHS, so over here I'll open the bracket and I'll get 1 times R of n minus R of n by n plus 1. So that 1 times R of n I'll move to the LHS, and at minus 1 over minus R of n over n plus 1 I'll use over here. So if you see, if you expand this expression, you will get this expression back. And now you have basically formed your deltas. So the LHS is delta of n plus 1 and the RHS is delta of n. So this is delta of n. And of course, you have this factor of minus 1 over n plus 1 sticking around. And now this recurrence relation is really easy to solve. So now we can just plug in a base case and it won't be very hard to find a general formula for these deltas. So what you get is, for finding the base case, this is the recurrence relation. For finding the base case, which we'll use as delta of 2, you can basically subtract R of 2 from R of 1 because that's how we define the deltas. So R of 2 is the ratio of D of 2 and 2 factorial. And likewise, R of 1 is the ratio of D of 1 and 1 factorial. And we saw that this is 1 and this is 0. So you get half. So delta of 2 is half. And now we can easily do a bit of induction. So delta of 3 is obtained by multiplying minus 1 over 3 to delta of 2. So you can see that over here. So if I want to find delta of n plus 1, where n plus 1 is what goes inside the bracket, that same thing which goes in the bracket also appears in this denominator. So if I want to find delta of 3, I divide by 3 and I take account of that minus sign. So I can rewrite that as minus 1 over 3 factorial. And likewise for 4, once again, this thing goes in the denominator. So you get 2 times 3 times 4. So 4 factorial, and negative of negative is positive. So you get positive 1 over 4 factorial. And you can easily see that this pattern is going to continue. It's basically the same pattern as factorials, except it's inverted. So in general, as I said, we get this simple expression. Delta of n is minus 1 over or minus 1 to the n over n factorial. And now we can find these R of n's, which are the ratios of the D of n to n factorial, using these deltas. So the delta is basically the difference between subsequent R terms. So I can write that expression, and if I rearrange, I get that R of n is R of n minus 1 plus delta, which makes sense because delta is the difference of these two. And now this R of n minus 1, I can write in terms of R of n minus 2 and delta of n minus 1 because this term is basically the difference of this and this. And then once again, I have an R term, so I can write it as the previous R term plus the delta. So I can keep going that way. And ultimately, I will stop when I reach R of 1. So you can see that here you have R of n minus 2, and then the deltas start at 1 above. So here I'm starting at, the R's are starting at 1. So the deltas will start at 1 plus 1, which is 2. So you have R of 1, delta of 2, delta of 3, and so on till delta of n. And then this R of 1 basically turns into 0, and the deltas, as we found the formula over here, just write it out. And then in summation form, you can ignore this 0 and you get this nice compact summation. So now we found R of n, and before we go forward to find D of n, you might remember that we had said that the ratio of D of n and n factorial should converge in the limit because they grow similar. So now that we have this expression for R of n, we can actually test that hypothesis and see if our conjecture was right. So I have written that down and I have changed this lower bound from 2 to 0. And that is allowed because the zeroth and first terms actually cancel each other out. You get minus 1 to the 0 over 0 factorial, which is 1. And then you get minus 1 to the 1 divided by 1 factorial, which is minus 1. So the sum is 0. So they cancel each other out and you are basically left with this one. So I've written it this way because this form is a bit more familiar. So if you take n to infinity, then this sum converges to 1 over e because it's the Taylor expansion of e to the power minus 1. So this ratio actually does converge and it converges to 1 over e. So if you write it in that subfactorial notation, because it looks prettier, you get this relation in the limit. So this is pretty surprising, but I hope that this you can see where it is coming from. It's basically coming from the delta sequence. So finally, we can wrap up by finding the expression for d of n, which is just simple multiplication of both sides with n factorial. So you get this formula for d of n. And a similar formula, which you can get with a bit of manipulation, is using the binomial coefficients. And this is the formula which you would get if you had applied the inclusion-exclusion principle. So if you don't know how that derivation using the inclusion-exclusion principle is done, you can try to do it on your own. And you should get an expression like this. So if you simplify this, you will get this expression back. And an interesting recurrence relation which pops out of this, but which is hard to prove combinatorially. I haven't been able to prove it combinatorially, and I have never seen anyone else do it either. So if you have a combinatorial proof, do let me know. But it so yeah, the interesting I was talking about an interesting recurrence relation which pops out of this formula which we have derived using R of n and n factorial. So again, you can try to prove it on your own using this formula. So you do a bit of manipulation in the expression of d of n and d of n plus 1, and you get this nice recurrence relation. And this is much more similar to the factorial recurrence relation because you have this multiplication by n plus 1 to get the n plus 1 term, but you have this extra term sticking around, which makes it different. But just looking at this term, you might expect that the difference of the factorials and the subfactorials is pretty small in the limit, but actually that's not the case. It grows pretty fast, and it actually grows as fast as the factorial itself. So that is something unexpected, which you might not notice at first sight without thinking much about it. So if you find a combinatorial proof for this yourself, or if you've seen it anywhere, do let me know. I'll be pretty delighted because I haven't been able to prove it and I have never seen anyone else do it either. So that's it. Thank you for sticking around. And here you can ask me any questions related to this if you want to. And I've given you some questions over here which you can try on your own to get a better understanding and to do some more self-exploration. And this fourth question in particular, I designed so that you see some relation between or some application of linear algebra in combinatorics. So you can take a screenshot of this if you want, but I'll be sharing the PPT anyway. So just to be safe, you can take a screenshot. Yeah, so here are some hints for the questions which I left as an exercise for the audience. And there are also some hints for these questions. So you can take a screenshot of this also if you want it for later. So here are some resources for further reading, which you can try out if you are interested in this stuff. And this article in particular will show you a different way of using linear algebra in combinatorics. So this will again evaluate the number of odd and even derangements, just like I have mentioned over here. So you can see that this question later goes on to mention the number of even and odd derangements. So that is something he has discussed in his paper as well. So you can check that out as well. So again, you can take a screenshot if you want. And anyway, this is the last slide, so I won't be moving forward. So if anyone has a question, you can let me know. If you need me to explain some idea again, or if you have some question which is related to this stuff but not covered. Okay, so in the chat, there is a question about u equal. Yeah, thank you for coming to the talk. and it was my pleasure. So about U equal to S naught, so that is actually just by definition. So as I said, the universal set is the ways of choosing elements in all possible ways. So we were choosing R elements from A elements. So of course the universal set is A choose R. And in the expression which we had, so maybe I'll go back in the slides. Yeah, here. So the first term is of course the ways of the all possible ways of choosing uh, our elements from A elements, and that is basically our universal set. So that has A choose R ways, and if you look at the expression for the sum over here, you see that S naught, which is the case of I equal to 0, is A choose R. So that's why we have that relation. So yeah, thank you everyone for attending, and I hope to see you again if I decide to hold another talk. So yeah, if we don't have any audience questions, we can end the call. So maybe we'll wait for a minute.
Hello.
Yeah.
Yeah, it was a great talk. I had one question. Somewhere you said that since A is a free variable, we can, I mean,
Hmm.
it does not give a free variable, we can replace it by anything.
Hmm.
Understand that?
Yeah, just a minute. Yeah, it was here, right? So the appearance of A does not add a free variable. That's what you're referring to, right?
Yes.
Yeah, so basically, what I'm saying is that in using these identities, we showed that if the difference of A and B is constant, then this S of A, B, R does not change. So over here, I've replaced B with A plus N. So A minus B is minus N. So that difference is constant regardless of what value of A you put. And we already showed that if A minus B is a constant, then it doesn't matter what the exact values of A and B are. If the difference is constant, the value of S of A, B, R is constant. So that's what I've said over here, that regardless of what value of A you put, the difference does not change. And that's why S of A, B, R does not change, even though it looks like it might change.
Okay. Thank you.
So any other questions? Okay, so I guess we'll end the call here. You
Yeah,
can
I
stop the
guess it's
recording.
about time. So if there are no further questions, we'll probably end it now.
Yeah.
And thank you all for coming. And thank you, Pranjal, for a very well prepared talk. I did not expect being reminded of textbooks again with an exercise for the reader kind of questions, but it
Yeah,
was.
well, that's the only way you can explore the ideas on your own.
So, yeah. Thanks to everyone for showing up
Yeah.
today.
And in the last slide, I have given my email ID. So if you need the PPT, you can send me an email. So it's just pranjal.jain at students.iserpune.ac.in.